So to develop an algorithm for unconstrained optimization, we need to find a good direction to move and a good step length, or decide how far we are going to move in that direction. And then we get a new point, and then we repeat this whole process. Then we again evaluate local information at x2. Based on it, either we decide to stop or move a little bit more, and then continue doing it. So that means we get a sequence of points x1, x2, so on and so forth, which hopefully should converge. To a desired point. That means a point which is the minimum. So like all algorithms, there are two sort of desirable properties of an algorithm. Number one is the algorithm should be correct. That means it should converge in a reason. Eventually it should converge. It should be correct, and when it converges, it should converge to a locally minimum point. And second, which is important but not as critical as the first one, is it should be fast. So it's easy to think of various algorithms of how you can move around in an n-dimensional space. You can choose some directions, then take some step length and move again, and then move again and move again. The difficult part is to actually proving that what you're doing is actually correct, and also analyzing how fast your method is. So the theory is required for both these two things, and sometimes it can be quite non-trivial and tricky. So we will try to look at some of the theoretical aspects of these algorithms as well. Okay, so coming back to derivatives. So recall that we have said that a derivative gives us an information about how fast a function changes around the given point. So a gradient is a sort of a vector that is given by, again this is quite informal, it's a column vector of partial derivatives of the function at that point. So it's an n-dimensional vector. If we are talking about a function of n variables, and how does it give us the local information that we want? So So given a direction S, the number S transpose gradient of f tells us how fast the function is going to change along S. Of course, this is locally, that means very, very close to f. So this whole vector is actually written as gradient of f. So if my function is 5x1 square minus 2x1 x2 plus x2 square, then the gradient of f, you should be able to evaluate. It should be some expression, a vector of size 2, and you should be able to evaluate it at a given point. So evaluating gradients of a function is not that difficult when the function is factorable or has some nice forms like sines and cosines and powers and exponents and polynomials. Then f can be gradient of f can be evaluated in almost the same time as the evaluation of function f, and there is a nice little theory about it. You can read something about automatic differentiation for finding derivatives of nicely behaved functions. So we will not go there, but we will just remember that taking derivatives is not that difficult. If you can apply product rule and chain rule that you might have read earlier, that might be enough to find derivatives of most functions that we will see in this course. And even in practice, differentiation is somewhat easier than integration. Okay, so what about the second derivative? So second derivative of a function is called the Hessian, and it is denoted as grad square f, and it's a matrix of size n cross n, and it has second order partial derivatives as its terms. So this is akin to your second derivative in one dimension, and it tells us how fast the gradient is changing along a certain direction. So given a direction S, so that means S is an n-dimensional vector again. S transpose grad square f times S. So this whole term would be a 1 cross 1, that means a single scalar, and this is the rate of change of the slope along S, along direction S, slope of F. So this is also called curvature. So if this value is highly positive, that means the gradient or the slope is increasing, and that means that after some time your function value may start increasing. So some methods actually don't rely on Hessian, but others rely on Hessian. Hessian computation is slightly more difficult than computing gradients, but algorithmically what you can try to do is just find the gradient of the gradient. So that means for every you just apply gradient again on this whole vector rather than on a function, and you will get n columns, one for each entry, and that will be your Hessian. Okay, so the book has some elementary relationships between Hessians and gradients for quadratic functions. Those are quite important. Please do try to read them, and also the explanations of what the Hessian signifies. So all that is quite important and will be needed in the later lectures.